Okay, folks, here we go with question number 9. As ever, I really hope you've done this question. If you haven't and you've got it in front of you, you could do it now, or just make sure you pause the question so you can kind of take in the question. I'm trying to not go too slowly over these in the interest of time. And as ever, please let me know if there's anything which is unclear. So we're looking here a kind of mechanics question, and I would call this a physics A question. Okay, we're looking at defining the moment of force. This is a nice one because it comes up again and again. All right, the definition of moments comes up a lot, and it's often very badly answered. Okay, a lot of students will define the moment as the turning effect of a force. Now, that is often something that a lot of teachers will use in their classes. Basically, the point here being that the higher the moment, the more something will rotate. However, if we're defining it properly, it is the product of two things. One, the force, and two, the distance. Now, specifically, we use this term, the perpendicular distance. What we're talking about here is the distance at right angles. So if you notice here, my force and my distance are at right angles to each other. They are perpendicular. So in order to get this mark, you must use that definition, not the turning effect, even though it's a nice one for describing what happens. Similar to that one, an often sort of badly answered question is the conditions required for equilibrium. Now, equilibrium, a lot of students again have the idea of what this means. It means that perhaps we're not moving, or we're not rotating, or we're not accelerating. And all of those are correct. And a lot of students will include that in their answer here. We don't need that in our answer here. What we're looking at here are how we achieve that not moving, that not accelerating state. And the way we do that is by two things. One, that we have a total or resultant force of 0. And we have a total or resultant moment of 0. In other words, everything is balanced. Okay, so we're looking for both of those, 1 mark for each one. All right, now we've got some calculations. Now, this is a really nice example of the difference between a 2 and a 3 mark question. Let's look at the first one here. Quite a complicated one. Okay, we've got a meter rule which is pivoted about this 22 centimeter mark. We're told that we've got an object of mass 40 grams. As soon as you see that grams, you should have a little red flag up on there. We've got 5 centimeters, could also be a thing here, okay, because we usually express things in meters, etc. Okay, so we've got a lot going on here. First thing we want to do is calculate the weight of this object. This is a 2-mark question, and that means that if it's 2 marks, you're just going to have to calculate something. I think it's a bit cheeky here actually. In previous specs you may have experienced this being a 3-marker. Why? Because there's an issue here with units. You're going to get 1 mark here for W equal mg. Weight is mass times gravity, gravitational field strength I should say. However, there's a little bit of a complication here, which is to convert this mass into kilograms. 40 grams needs to be turned into 40 times 10 to the minus 3 kilograms. You're going to multiply by g, which is 9.8, not 9. And you get an answer here of 0.39, and that's why the weight here is 0.39 newtons. Okay, so that's an example of a 2-mark calculation question. Let's have a look at a 3-marker. We're now going to calculate the weight of the meter rule, and to do this I'm going to just explain what's going on here. We notice here we are in the equilibrium state, and that's why the previous question asked us about equilibrium. This means that the moments must be balanced, and we're going to use that in order to calculate the weight of the ruler. We notice here we're going to use the idea that the moment in the anti-clockwise and the moment in the clockwise direction must be balanced to each other. Now, the object is providing an anti-clockwise moment. If the object was acting just on its own, it would cause the thing to spin around this way. What's balancing that is the moment due to the weight of the ruler itself. Now, that weight is x, and it acts from the center of mass. In other words, the 50 centimeter mark. Right? And you can see why this is a 3-mark question. We're going to remember that this distance here is 22, that from here to here is 50, and so that our center of mass, or center of gravity if you want to call it, is 28 centimeters from the pivot. We now have a force and a distance time plus another force and another distance. We're going to calculate our moments. So we'll just scroll down. We notice we've got it here. That 0.39, that's the weight, times 17, which is the distance of the object from the pivot, is equal to x, this unknown force, times 28, which is the distance of application of that unknown force. Okay, now we've got all the values we need to calculate there, and we find that we've got a weight of 0.24. Okay, now hopefully you can see here why this is a 3-mark question. Right? You are being asked to use moments. You would definitely get a mark for using moments. Okay, but where you get the extra marks is for identifying these distances and making sure that you're comfortable with the values of distance, identifying the location of the center of mass, and that gives that extra difficulty, which is why it's a 3-mark question. Okay, as I've said a few times, this is very much a classic question, very much sort of repeated one. So if you're not sure about this one, please make sure you go over it and have a look. And if you've got any questions, let me know.